Hi again, welcome back. In this video, we focus on the geometric sequences and series, and we develop ideas to create and use a general term. The approach parallels that we used for the arithmetic series. We now examine the second of the two types of series we discussed in the introductory video on this topic, and that is the geometric sequence or series. Take the numbers 2, 4, 8, 16, 32. There is a common ratio between successive terms. And to calculate this ratio, we divide a term by the one before it. So 4 over 2 is 2, and so on, up to 32 over 16 equals 2. So we are determining how we move through the sequence, and that is by multiplying a term by 2 to get to the next term. A geometric sequence has a common ratio between successive terms. If we write a geometric series, then we use plus signs between the numbers rather than the commas we used in the sequence. So for example, we have 2 plus 6 plus 18, etc. We can also refer to a geometric progression for a set of numbers, and by doing that we simply imply that there is a common ratio, and we write the progression down in the same way as we would with a sequence. Now we can look at this series that we wrote before and analyse it in the same way as we did for the arithmetic series. So the first term, which we'll call T1, is equal to 2. The second term, which is T2, is 6, and that is 2 times 3, or 3 to the 1 if you want to start the pattern. The third term, T3, is 18, which is 2 times 3 times 3, because it's 6 times 3. So we can rewrite that as 2 times 3 squared. The fourth term, T4, which is 54, becomes 2 times 3 cubed. The fifth term, T5, becomes 2 times 3 to the fourth. So we're looking at the pattern of the term number and the index for the common ratio. And there's a 1 difference. So we can say for the nth term, Tn, we've got the first term, T1, times the common ratio, r, to the n minus 1. So to remember it, say it pretty much like I've just said there, because for me that's going to be automatic. The nth term equals the first term times the common ratio raised to the power n minus 1. A typical question we might be asked is to find a particular term. So we might be given the geometric series 3 plus 6 plus 12 plus 24, and we have to find the 10th term. So write down T1, which is 3. We find the common ratio, 6 divided by 3, which is 2. So T10, the 10th term, is the first term, 3, times the common ratio, 2, to the 10 minus 1, or 9. Multiply those in your calculator, 1,536. If we wanted the 11th term, then we would take the 10th term and multiply it by the common ratio, 2. That would give us 3,072. If we want the 13th term, which is another 2 along from the 11th term, then we're going to take our 3,072, multiply it by 2 to get the 12th term, and then another 2 to get to the 13th term, 12,288. If we wanted to go back the other way to find the 9th term, then we would take the 10th term, divide it by 2, and we would get 768. Nice to remember this pattern. Very important that you can see the way in which you can move from one term to another. Just as we did for the arithmetic sequence, we can also pause here to look briefly at the computing formula for the nth term that we have just developed. So the nth term is equal to Tn, which is T1, first term, times r, common ratio, to the n minus 1. Which is, if we put it in different symbols, we could say that y was equal to some constant c times r, the common ratio, raised to a particular power. So we can see that the two equations have exactly the same format. That is, the nth term of the geometric series has the same format as the basic format for the exponential equation. When we look at that similarity, we can see that the common ratio of the geometric sequence is just the base of the exponential equation. A common question, apart from finding the nth term of course, is how many terms are in the geometric sequence, and they'll give you a geometric sequence. The one I'm using is 6, 3, 3 over 2, up to 3 over 64. So always the same approach. Write down T1, the first term, which is 6. The common ratio is 3 divided by 6, which is a half. And then we say, well, the last term, Tn, is 3 over 64, so write that down, and that's equal to the first term, 6 times the common ratio, which I'll write as 0.5, to the n minus 1. So now divide both sides by 6. We have 0.5 to the n minus 1 equals 3 divided by 64 times 8, which turns out to be 384. We then change from our exponential form to our log form, and also use the opportunity to change the base. So we have n minus 1, which drops down from the index, equals the logarithm of what was previously the right-hand side, logarithm of 3 over 384, divided by the logarithm of 0.5. Put all that in your calculator, you get 7. N minus 1 equals 7, so therefore n equals 8. So the 8th term is 3 over 64. Another common question, which parallels that we encountered in the arithmetic sequences, is if the 4th term of a geometric series is 192, and the 12th term is 12,582,912, find the first 3 numbers of the series. Don't worry about the big numbers. They're just going to go into your calculator. You don't have to do anything with them in your mind. So write down what we've got. T4, 4th term, is equal to 192, and we know that we can write that as the first term times the common ratio, R, to the 4 minus 1, which is 3. Similarly, T12 is equal to 12,582,912 is equal to the first term, T1, times the common ratio to the 12 minus 1, which is 11. Now just divide them. T12 divided by T4. We have 12 million, etc., over 192, and the T1s cancel out, so we're left with r to the 11th over r cubed, which is simply r to the 8th. Put it into your calculator and calculate the 8th root, and the r turns out to be 4. See? Easy. We didn't have to get concerned about anything. So 192, going back into our T4 statement earlier, 192 is equal to T1, the first term, times our new common ratio, 4 cubed. Put it into your calculator, T1 is equal to 3. So the first term is T1, which is 3. The second term is T1 times our common ratio, 3 times 4 is 12. And then the third term is our 12, which we've just calculated, times our common ratio, which is 48. So it's 3 plus 12 plus 48 if we're looking for the series. See? Nice and straightforward. Always the same. Some questions simply state that we have 3 terms and we're told that they form a geometric sequence or series. In all such questions, remember that if it's a geometric sequence or series, that implies there's a common ratio. So the question's simply saying, hey, you determine the common ratio. For example, we might be given the numbers y minus 1, y minus 10, and y plus 8, and we're told that these form a geometric sequence. So find the values of the first 3 terms and the next term. If they form a geometric sequence, there's a common ratio. So just find what the ratios are of the three terms. So y minus 10 divided by y minus 1 is one form of our ratio, and the other form is y plus 8 divided by y minus 10, and we know that they're exactly the same. So multiply both sides out, so we get rid of the fractions, 8 fractions. So we get y squared minus 20y plus 100 equals y squared plus 7y minus 8. The y squares cancel, leaving us with 27y is equal to 108. Y is equal to 4. So now we can substitute back into our sequence that we were originally given. Y minus 1 means 4 minus 1, so our first term is 3. The second term is y minus 10, which is minus 6, and our last term is y plus 8, which is 12. So we have a sequence of 3 minus 6, 12, and the common ratio, of course, is minus 2. So the next term is going to be 12 times minus 2, which is minus 24. Nice and straightforward. Geometric series, so geometric sequence tells us we have a common ratio, so respond in that way. So to summarise, a geometric sequence or geometric series has a constant ratio between consecutive pairs of numbers. The sequence 5, 30, 180 and so forth has a constant ratio of 6. The sequence 125, 25, 5, 1, etc. has a constant ratio of 1 over 5, because it's 25 over 125, etc. The general term, i.e. Tn, of a geometric sequence or series is determined by the nth term being the first term multiplied by the common ratio raised to the power n minus 1. And if you wanted to put that down formally, we can say that Tn is equal to T1 times r to the n minus 1. So you should now have the steps to be able to develop and use the approach for the nth term for a geometric series. Hope I have helped you to clarify the concepts underlying that. Thanks for watching this video. In the next video in the series, we look at the way in which we can develop strategies for the sum of n terms of a geometric series. Hit the like button and subscribe if you haven't already. Also, go and do some questions in test 1 on my website, drjaysmaths.com. Just click the back arrow and you'll get there. Add a comment or send me an email if you have any questions. Good luck with these. See you later.